Hello, Rotary International. We're traveling the galaxy today. We've got our first guests. Thank you for joining us here on a Friday. Are we really lost in space? Just kidding. We're live here from One Rotary Center in Evanston, Illinois. Thanks for joining us today. It is actually the 49th anniversary of the moon landing. And today we're going to be joined by Fabio Pacucci, Yale astrophysicist and Rotary member. Fabio has been doing some amazing work on black hole research. So if you have any questions for him, leave them in the comments below. We'll be taking some of your most engaging questions, whether that's about deep space or what it means to be a good citizen and people of action here on Earth. So Fabio should be joining us any minute now. So as you guys know, this is a part of a new series we're doing called Between the Lines, where we take you inside the stories of the Rotarian magazine. We'll be featuring different people every month, either that's photographers or writers, some of the subjects featured. If there's anyone in particular that you'd like to hear from, please write us in the comments and we'll consider it for a future episode. Yes, we would be happy to put a schedule going forward of when you guys can tune in for episodes. Right now we're thinking about the second week of every month. If there's a particular date that you would like to see us interview someone, like a national holiday, just let us know. Hello, greetings from Ecuador, and hello from Pakistan. So for those of you just tuning in, we will be live with Fabio Pacucci, Yale astrophysicist and Rotary member. Right, we're just waiting to connect. Hello, Fabio.
Hi, good morning, everyone. How are you?
Doing well, thanks. How are you?
I'm good. Very well. Greetings from Yale.
How's Yale today?
Oh, it's pretty cloudy, a bit, but
Same here.
most of the people are on vacation now, so there are not many students. So it's pretty quiet this period.
Well, thanks so much for joining us today.
No, thank you for inviting me. It's a pleasure.
So, starting off, we were curious if you could answer, what are some misconceptions about astrophysics?
Yeah, that's a very interesting question. So sometimes when I go and do like outreach events, I witness how sometimes people have very strange ideas about the work of an astronomer or of an astrophysicist. So one of the most common misconceptions is that, of course, astronomers live at night and sleep all day, while this is true for a very small fraction of the astronomical community, the people that actually work at the telescopes, but most of us actually have a very normal working schedule. And I personally sleep all night and I work at day like most of the people. Another misconception sometimes related to this is that people think that astronomers obviously work at telescopes. I very rarely see telescopes because personally, I'm a theorist. I do theory, so I try to interpret the observations that people do at telescopes. But actually, of course, there are astronomers, observers, as we name them, that actually work most of the times at telescopes. Another funny, from my point of view, misconception is that astronomers obviously know all the names of the stars we see in the sky. So people, sometimes we go out and the people ask me, so what's the name of that star? I might know it, but sometimes it's very unlikely because, for instance, in my work, I don't care about stars at all. I don't work on stars. I work on black holes. And anyway, the stars that we see in the sky, they are very interesting for many reasons, but we really don't need to know the names of all the stars that are there. And the last one, maybe that I was thinking about yesterday, is that usually in the US, many people tell me, so are you an astronomer? So you obviously work at NASA, which is not true, because all over the country there are many institutions, both private and public, that develop research in astrophysics and astronomy, and they are not NASA, while there are many astronomers that work at NASA as well, of course.
Thank you for clearing that up. I think you answered some questions I've had as well.
Yeah.
So let's talk more about your research specifically. Your research aims at understanding the properties of the first black holes formed in the universe. So how did they form?
So the honest question is that nobody knows. Otherwise, I wouldn't get my salary, because we still have to find out. But, well, to form a black hole in general, so not necessarily in the very early universe, but also in the local universe, so around us, we need massive stars. So the story that sometimes we also teach in high school or college is that very massive stars lead to the formation of a black hole at the end point of their evolution. So they explode as supernovae and they collapse into black holes. This is true, and the problem is that concerning the early universe, so what I study in particular, is that in the early universe, so billions and billions of years ago, we already observe supermassive black holes. So black holes that are billions and billions of times more massive than our sun. So these are real monsters in the universe. So the fact is that we observe them both in the local universe, so around us. For instance, in the center of our own galaxy, the Milky Way, there is a supermassive black hole. But we observe them also very far away, so very early in the history of the universe. And the question is that we really don't know how it's possible to form them, since if you start from a small black hole, so black holes that we know how they form, they need a long time to grow to very large scales, to supermassive scales. So a black hole can grow basically by two channels. Either a black hole can accrete mass, so it can swallow mass from the surrounding environment, can heat planets, gas, stars sometimes, and it grows in mass. Or black holes can, to some extent, collide together and grow bigger. The fact is that to reach supermassive black hole scales, so billions of times the mass of the sun, you need sometimes billions and billions of years. So we really don't know how it's possible that we observe supermassive black holes when the universe was less than 1 billion years old. So there are basically two possibilities. So either the first black holes were formed when very massive stars at the beginning of the universe collapsed, exploded maybe in supernova, and formed these black holes that in some ways grew up very rapidly. Or what I study in particular is an alternative channel to form very massive black holes, and that could happen only at the beginning of the history of the universe, so when the universe was very young. And so if you take a cloud of gas, a very massive cloud of gas at the beginning of the universe, under some conditions it's possible that this enormous cloud of gas can collapse and form instantaneously a very massive black hole of several 100,000 solar masses. And that could, to some extent, ease the problem of forming supermassive black holes very early in time of the history of the universe. So this is basically what I study. I try to understand how to form extremely massive black holes in a very short time, just to complete.
That's incredible. Thank you for sharing. You touched on something that I had noticed before in one of my favorite films, Interstellar, about the accretion disk. Is that correct?
Yes.
I was curious, how do films like Interstellar get black hole depictions correct, and maybe how they've inspired laymen to learn more about astrophysics?
Yeah, of course, Interstellar is one of my favorite films. It's an interesting story, but what what interests me more is that it offers, as you were saying, a very realistic depiction of how we would expect a real black hole to be. And so how it's possible that they reached this accuracy in the depiction of a black hole? Well, one of the producers of Interstellar is Kip Thorne. Kip Thorne, Professor Thorne is a world-famous astrophysicist. He won the Nobel Prize for Physics for his studies on gravitational waves, so waves emitted by the collision, to some extent, of black holes. And he also worked with Stephen Hawking. He contributed to the black hole theory in a lot of ways. And specifically when it comes to Interstellar, he supervised the visual effect in Interstellar, in particular the rendering of Gargantua, the supermassive black hole. So what we see, the depiction of Gargantua, is very realistic because partially it comes from real astrophysical simulations of how a black hole should be. For instance, we see that the accretion disk depiction, as you were saying, is very realistic. We also see some general relativistic effects that, with the eye of an astronomer, are very visible in the way light moves around Gargantua, the black hole. And to some extent, it's similar to what we expect to see in a few months when the data from a worldwide experiment that is named the Event Horizon telescopes will come to us. So what we are trying to do, it's a huge international collaborations, many telescopes all around the world. They are trying to have the first image of a black hole. Black holes have never been observed directly. In this case, we are trying to have the first image almost of the event horizon of the telescope, so the inner part of the black hole. And in particular, we're trying to image the supermassive black hole that is close by, so the one at the center of the Milky Way galaxy, because it's very big and it's sufficiently close. So what we are trying to observe with the Event Horizon telescope is, to some extent, what we saw in Interstellar. And it's surely an inspiring movie for the general public, and it also inspired a lot of people to learn more about of the weirdest effects about black holes, like time dilation and gravitational tides in the water planet. So to conclude, it's a very interesting way to inspire people to learn more about these very strange objects.
Thank you. That's actually a question we just got from our audience, is what's one of the weirdest effects that a black hole can have?
Well, maybe it's time dilation. So the fact that for a faraway observer, when another observer gets close to a black hole, for instance, it lands on a planet that is orbiting around a supermassive black hole, then what happens is that the time how the time passes for the distant observer is very different from how the time passes from the astronaut that landed on the planet very close to the supermassive black hole. And that's a general relativistic effect for sure. And so we have a factor of difference between how the two times are passing that becomes very important. We saw it in the movie, for instance, a few seconds passed on a planet very close by to the supermassive black hole equals to many years passed, for instance, on the Earth. Well, another one is the tidal effect. So the fact that, for instance, on a planet very close to a supermassive black hole that is made of water, there are huge tides, and we actually expect them. It's actually very realistic, and that's one of my favorite scenes on the movie. It's very dramatic.
I was curious about a phrase we saw on your website, the Latin phrase per aspera ad astra semper, which translates to through hardship to the stars always. Could you tell us why that phrase resonates with you?
Yeah, it's one of my favorite Latin quotes since high school. So I'm Italian. I moved here a couple of years ago. So in Italy, we study a lot of Latin, especially during the high school. And a similar quote appears in many ancient authors like Virgil or Cicero, Cicerone in Italian. So it resonates with me because my work is literally reaching for the stars. And because in life, many times to achieve big things, it's necessary to go through some difficulties. So to some extent, I believe that it's not valid only for my own job, but for everybody's life. So to achieve big things, it's important to go through hardship.
It's lovely. Speaking more about that, you know, hardship and problem solving and rising up in your own community, could you talk to us a little bit more about how you became interested in Rotary and how you got active in your community?
Yeah, sure. So my first encounter with Rotary was at the end of my high school. I was in Taranto, a little town, or well, a little city in the south of Italy. And so I won a prize at the end of my high school. So I went to the Rotary and to get the prize. And they invited me to join the Rotary at that moment, but I wasn't moving away from Taranto. I went to Rome to study for my bachelor and the master. Then I moved away again for the PhD. So I didn't really have time to join one Rotary community in a stable way. So once I got to the US, now I'm an astrophysicist here at Yale, I thought that it may be finally the time to stabilize a bit and to contact the local community. So I'm part of the Rotary of New Haven. It's a wonderful environment, a wonderful community in which many people of different from different backgrounds with different experiences can share a lot and actually act in the world in an important way.
Thank you. We had a few other questions from the audience. Let's see. Oh, when are we taking Rotary to space? Hopefully soon. I would love to see Rotary on the moon or at Mars. How
like
about
on the space station? Well, that would be very, very expensive.
How about another one? Someone asked, is the Big Bang Theory true?
Well, the Big Bang Theory is certainly the theory that describes the observations of the universe that we have so far in the most accurate way. So we do have a lot of observation, like the fact, for instance, that the universe is expanding at an accelerated rate, and that are perfectly described by the Big Bang Theory. So the Big Bang Theory, in very simple words, is that the universe started in a singularity. So a singularity is an event of infinite density, basically. So what happens is that there is a kind of an explosion, but it's not a real explosion because there was nothing before the Big Bang to actually the Big Bang explode through. So the universe started in a singularity, a point of infinite density, and it started to expand into nothing, basically. So we do have a lot of observations, for instance, the cosmic microwave background, so the relic radiation that we see at a particular frequency all over the universe, or the fact, as I was saying before, that the universe is expanding. We have overwhelming observations about that indicate that the Big Bang Theory should be actually the correct depiction of the universe as we know it. Of course, we're talking about science, so nothing is certain. Everything can be disproved by other observation, but we can be pretty certain that the Big Bang Theory is a very, very solid theory to describe the universe as we know it today.
Thank you. We have another one from the audience. How did you first become interested in being an astronomer, astrophysics? What caught your attention about space?
Well, I was always interested. I don't remember a particular period in my life in which I didn't love stars. So I remember that my parents bought me a little telescope when I was 5 years old, and then from that I started to look at the stars, to look at the moon, for instance, to go out with my parents or with my friends to look at the stars, the shooting stars, for instance. Then at the high school I did more project about astronomy, and then I chose to study physics and astronomy and then go on with this profession. So it's never been really hard for me to choose my profession in life because I really loved it since the beginning.
And do you feel like your experience with Rotary, with meeting new people from all over the world, I mean, has that helped you to build better international relationships with, your counterparts at institutions around the world?
Yeah, sure. But the experience with Rotary in New Haven in particular allowed me to meet many interesting people with different life experiences, as I was mentioning before, and different backgrounds. And for scientists, it's very important to meet with people who think differently. So historically, science has always flourished when people from different countries, different societies, and different habits have met to achieve something greater. So this is valid not only for science, of course, but as also the Rotary Society proves in every aspect of the human endeavor. So societies, organizations like the Rotary that put people together to achieve something greater are very important for the development of society in general and not only of science.
Thank you. Well, today is actually a pretty important day. It's the 49th anniversary of the first manned mission to land on the moon. We were curious, what do you think the next 50 years of space exploration might look like?
Yeah, so it's extremely hard to predict what the future of space exploration may bring because as human enterprises, most of the times it depends on many factors that are not connected to science at all. For instance, in the 1960s, the US brought the man to the moon also to win the space race with the Soviet Union. So there are other like factors to take into account, like political factor, economical factor, military factor. So nobody really knows what are the political, economical, and what would be the scientific situation in like 50 years. But of course, there is something that can be said about this. So space exploration has changed dramatically in the past 50 years, and nowadays space enterprises have become so expensive that they require the collaboration of many countries to be achieved. For instance, the International Space Station, a space station that is permanently inhabited by astronauts, and it's about 300 kilometers above our heads. It's an extremely expensive enterprise that cannot be achieved by a single country anymore, but needs the collaboration of many countries. So in addition, another factor that has changed very much in the past 50 years is that we now see the rise of private space enterprises. For instance, SpaceX, that is very famous nowadays for several reasons. And this is completely changing the exploration scenario in ways that are very hard to predict in the long term. But sometimes we say that instead of sending humans to space like the US and other countries did in the 1960s, for instance, it would be much better to send just robots because they are cheaper, for instance, and safer for several reasons. And this is certainly true, but on the other hand, it's also true that the inspirational power created by actual human beings being sent on the moon, for instance, or exploring space is something that robots will never achieve. So we will see in the next 50 years what science and other factors will bring to us. It will be exciting for sure.
Well, what's next for you in your research? Are there any projects on your horizon you could tell us about?
Oh, well, my research is basically the final goal of my research is to find one of the first black holes that formed in the universe. So currently we are targeting a very interesting source that is named CR7. So CR7 means Cosmos Redshift 7. So it's a very far away galaxy. It's billions and billions of light years away from us. And there are several reasons why this galaxy is interesting for our purposes, because looking at the spectrum of this source, so what kind of light it emits, it's a very weird source. So it has many features in its spectrum that may indicate, for instance, the presence of one of the first black holes that formed in the universe. So there are many objects out there in space, and our work is to build theories that can describe the light that they emit, and then go out there and look with telescopes and actually find the signature that we predict for these sources in the real world. And so my final goal, at least for these years, of course, until we discover something, is to have actually a clear signature of one of the first black holes that formed in the universe.
Well, thank you so much for your time today. If people want to learn more about your research, they can find out more about your website, right? FabioPacucci.com, FabioPacucci.com.
Thank you. Thank you very much for having me.
Thank you. And guys, tune in next month as we go between the lines of the Rotarian magazine. Leave your comments below for what you'd like us to focus on next. And be sure to like, comment, and share on Facebook, Twitter, and Instagram. See you. Bye.
Bye.